Hi everyone, myself K. Gurucharan. Now I am here to tell about silicon carbide. Introduction to silicon carbide devices in power electronics. The main aim is to tell about what are the silicon carbonate devices, advantages of silicon carbonate devices, applications of silicon carbonate devices, and challenges in silicon carbonate devices implementation. Let us discuss about what are the silicon carbide devices. Silicon carbide devices are semiconductor components used in power electronics with enhanced performance characteristics, including higher temperature tolerance, faster switching speeds, and lower conduction losses compared to the traditional silicon devices. Here are some silicon carbide devices used in power electronics are silicon carbide diodes, silicon carbide MOSFETs, silicon carbide JFETs, silicon carbide IGBTs, and silicon carbide power modules. Working principle of silicon carbide devices. The working principle of silicon carbide devices such as the silicon carbide MOSFETs or silicon carbide diodes lies in the unique properties of silicon carbide as well as the wide bandwidth semiconductors. When the voltage is applied, the silicon carbide devices allows or blocks the flow of electric current based on the control signals. In silicon carbide MOSFETs, for example, the applied voltage is gate terminal creates an electric field, enabling and inhibiting the flow of current between the source and the drain terminals. This process results in the efficient power switching with the reduced conduction and switching losses, contributing the higher performance and the efficiency of power electronics applications. The advantages of silicon carbide devices are high temperature, high power density, reduced overall system size, reduced overall system cost, and more reliable in high temperature environment, and reduced power losses by more than 50%. Applications of silicon carbide devices are power electronics and inverters, electrical vehicles, EVs, renewable energy systems, industrial motor drives, high frequency RF devices, power supplies, medical electronics, and rail transportation, and etc. The main challenges or drawbacks in the silicon carbide devices implementations are manufacturing cost. The production of silicon carbide wafers and devices is currently more expensive than the traditional silicon based devices. As a result, upfront cost of silicon carbide devices can be barrier to the widespread adoption, particularly in the cost-sensitive applications. Scale of production. The scale of silicon carbide device production is smaller compared to the silicon device. Increasing production scales is crucial to achieving the economics of scale and reducing cost. Material defects. The production of high-quality silicon carbide wafers are challenging, and its defects in the material can affect the device performance. Gate oxide reliability. Silicon carbide MOSFETs requires a gate oxide layer, and ensuring the long-term reliability remains a challenge. Gate oxide issues can impact the overall performance and reliability of silicon carbide devices over time. Transportation period. This period poses a challenges in terms of compatibility and the need for the dual infrastructures in some areas and cases. The conclusion to the silicon carbide devices are silicon carbide devices represents the transformative technology in power electronics, offering advantages such as high efficiency, faster switching speeds, and enhanced thermal performance. While facing the challenges in terms of manufacturing costs and the standardization, ongoing advancements continue to the proper silicon carbide devices towards the broader adoptions, particularly in the applications such as electrical vehicles and renewable energy systems and the higher power electronics, where their unique properties contribute to improved performance and reliability.